Thank you very much. So first of all, I would like to join other speakers in thanking the organizers. It's a real pleasure to be here. I think it's a wonderful workshop atmosphere that we have here. So thank you very much for making this possible. Yes, so I come from New Zealand. This is our campus in the suburbs of Auckland. It's also a nice place, quite different from Brazil, but also nice, and it took me a long time to get here. But apart from that, let's get on with the talk. So I'm planning to talk about two things today. So the first part of the talk will be solitons in the one-dimensional Bose gas, so working with integrability here. And then the second part will also be about one-dimensional quantum gases, but from a much more technical and maybe brutal perspective, looking at how to accelerate the convergence of exact diagonalization expansion. So we will talk about it when we get to it. So first, solitons. I assume most of you will be familiar what solitons are. Usually we find them in the classical world in terms of water waves. So there's a localized water wave here that you see in front of the beach. You can find them in other nonlinear wave systems. Here, coupled pendular in Bose-Einstein condensates that were seen in nonlinear optics. Of course, they're well known. Now. Just as a cartoon picture on how do you get to solitons and nonlinear waves, let's start with a well-known wave equation. Here the nonlinear Schrödinger equation is the most relevant one. And then you can find some of these nonlinear waves by continuation from linear wave solutions, well-known linear wave solutions. For example, if here this nonlinearity parameter G corresponding to interactions in Bose gases, for example, is turned negative, attractive, then you will have a deformation of the cosine wave here to Jacobi elliptic functions, and eventually you can take even the boundaries away and get a hyperbolic second, which is a localized wave solution. So in repulsive interactions or defocusing nonlinearity, for G larger than 0, you see other types of deformations, other type of Jacobi elliptic functions, but in this case here a node is preserved and becomes a localized wave that can travel along a background of constant density in this case here. Right, so these are the nonlinear waves, in particular so well-known bright and dark solitons. So the nomenclature here comes from optics. Bright solitons is just a bright spot of light, and dark solitons is a dark spot where you don't have light on an otherwise background. So they arise due to a competition here between dispersion and nonlinearity. Yeah, so this is the way it is explained in terms of nonlinear wave physics. Partial differential, nonlinear partial differential equations. Now, there are lots of similarities between bright and dark solitons. They arise from the same equation. There are also quite a lot of interesting differences, which will become important later. For example, here the bright soliton solution, there is essentially one, or it's a parameter maybe that is the amplitude. So here is one that is not moving, has a constant flat phase background, and then because the equation is Galilean invariant, it's a Galilean invariant system, you can give it a Galilean boost and you get a moving soliton. Right, so this is, in some sense, it's quite simple and much more simple than for dark solitons, where you also have a family of solutions that are characterized by their velocity. So there's a background that is already fixed, let's assume, and then you still have solutions that have zero velocity, that have a phase step of pi, and you have other solutions that have a phase step which is different from pi, and they will move at some velocity relative to the fluid. Okay, so this is not just a Galilean boost, it is quite a non-trivial object. Okay, so I want to talk about then how to find these solutions from the beta ansatz, so from actually in an interacting many particle system. But let's first start with bright solitons and mention that there are experimental investigations of bright solitons in the context of ultra-cold gases, which is where I usually work. So first experiment go back to 2002, and then there's been a number of them. Just to, so Markus Oberthaler, who spoke here a couple of days ago, for example, also had an experiment in that direction. Let's just mention a fairly recent experiment by Randy Hewlett's group that created quite a lot of these bright solitons and then observed their dynamics in time by a method called phase contrast imaging. They can actually now image the same sample several times after the other, so they can actually see what follow the time evolution. And so one of the things that at least are, well, seem to be still puzzling, they were already came up in the early 2002 work, is that it looks like there's indications in the data that solitons, their collisions depend on, what collisions look like on these pictures depends on the relative phase of these solitons. And the experimentalists think they see that they are repulsive and more often repulsive than they should be. So then this is interpreted that the phase, that there is some kind of phase locking or some bias in the relative phase to be around pi rather than 0. So that is sort of a bit of a mystery still, I think. I have my own opinion about it, which I won't say here, but so when I have some results, I will write a paper about it, I think. Okay, and apart from that, there are also there's a lot of interest in going into a regime of quantum solitons where you can actually see quantum effects. I mean, there are other unanswered questions here about losses, but I don't want to talk about that either much more. Okay, so what are quantum bright solitons? So what is the quantum theory of solitons? Let us start in the Lieb-Liniger model. So we have now bosons moving in one dimension with contact interactions. Okay, so main difference from many of the talks that we heard this week is that it is a continuum model. There's no lattice. So there is real translational invariance. Interactions here are modeled by the delta function. Okay, now early solutions came here by McGuire in 1964, who found exact solutions. In particular, there is a bound state of n particles. It does not have any bound excited states. Any excited states are scattering states. And then, of course, so this doesn't require specifically a beta ansatz, but of course it is related to beta ansatz. So then, full theory of what experimental, what should actually be relevant for experiments or for something that people see in experiments was done slightly later here by Vadati and in particular Lai and House. Did very good work predicting that there is a center of mass spreading and a phase drift. So this phase drift or phase squeezing was also discussed in the context of optics. And there were some experiments, particular here, early 90s, already that saw some squeezing and phase drift of the phase in solitons in optics, which are pure quantum effect. Yeah? So these are effects that cannot be explained by mean field theory, by the nonlinear Schrödinger equation itself. Okay. Now, so what are quantum bright solitons? First of all, the eigenstates of that equations are bound states of n bosons, the relevant eigenstates. Now, of course, because we have translation invariance, we can always separate, if we have n particles, we can separate off the center of mass. That becomes a free particle, motion of a free particle. the eigenstates have, well, the center of mass would be in a momentum eigenstate, yeah? 0 for the ground state, for example. And then moving solitons would just be Galilean boost to the center of mass, but otherwise nothing happens. So in order to have something that is localized in an experiment that is observable, you would have to create a wave packet with different center of mass momenta, for example. Or if you want to have a definite phase, as is relevant in optics, you would want to have superpositions of different particle numbers. Okay, so, but that you have a wave packet of the center of mass also means that over time the center of mass would spread, so that has not been seen or observed as far as I know. There's some non-trivial predictions here that say you could create a Schrödinger cat state by scattering a soliton of a very, very tiny impurity, essentially, that does not affect the relative wave function, does not affect the bound state, but just basically does some interferometry on the center of mass and splits that in two. I think that would be very hard experimentally to do. What is currently being investigated, also in experiments, I think by Randy Hewlett, is doing an interaction quench, which, and then the prediction is a soliton should, well, in the classical equation, the soliton should develop into a breather. A breather is a superposition of two solitons in some sense. But if you work with, with the exact solutions, you find that there is a certain probability for these solitons to have different velocities, so they could spread. Okay, so this is something that people will try to measure experimentally. Okay, now let's look at the single particle density. So what I'm doing now seems fairly simple, but it's sort of a build-up to what we will later discuss with dark solitons, where things are a little bit less trivial. So the single particle density, so we want to look at, so it has a shape, okay, depending on what the center of mass wave function is, of course, that depends, but for the bound state, you have already this shape, and then the center of mass also does something to it. So when you look at the variance, for example, it is not very difficult to prove that the variance of the single particle density here is a sum of a variance that just comes from the bound state and variance of the center of mass wave packet. Okay, and the center of mass, if it is a Gaussian wave packet, then it will evolve in time, and the time evolution is just that of ballistic expansion of a Gaussian wave packet. Right, so not really any surprises here. Okay, and I just want to mention briefly that the off-diagonal single particle density matrix is not so easy to compute from beta ansatz as people may know. So I had a project student, actually a summer student, who was with me a couple of years ago, and he developed a diagrammatic approach based on the coordinate beta ansatz to calculate this, the center of mass. The full single particle density matrix. And that is sort of nice, because when you have that information, you can see, well, how strongly correlated is that state actually. So it is almost nearly a Bose-Einstein condensate if the center of mass is localized on the same size as the single particle density, but then as it spreads out over time, this condensate fraction will reduce. Okay, now let's go to the main topic here, to dark solitons, where things are interesting, maybe a little bit more interesting because they're a little bit more difficult to describe. Okay, so first of all, the classical solutions are just solutions of these equations, were found here by Tsutsuki. So we have zero velocity dark solitons which have a localized dip, the density actually goes to zero. The density does not go to zero for moving solitons, and there's a superfluid phase step that is quite relevant, as I already mentioned. Now, experimentally, they were also observed and seen in Bose-Einstein condensates, so there were a number of experiments which I'm not completely listing here. I'm just showing some data. So this is actual data taken from an experiment in Klaus Senkstock's group, where they created a dark soliton, and this is on an inhomogeneous density profile, which is given by the trapping potential for their Bose-Einstein condensate. And you see this dark soliton move and oscillate across this density profile. So it goes back and forth, and then you can extract its trajectory, extract frequency. And the frequency of these oscillations is now smaller than the frequency of the trap, of the harmonic oscillator trap. The factor here is, of the square of these frequency ratios is 2, which was predicted by theory. Again, this comes out of the nonlinear equations, but it can be interpreted quite nicely as a ratio of the inertial mass of the soliton, which can be computed from its dispersion relation, to a quantity called the physical mass. It can also be calculated from the dispersion relation, but it essentially is the mass of the particles that are missing now. If you integrate over this dip in the density, you get a number of particles that is missing there, and multiply that by the bare mass of the constituent particles. Okay, so these are the classical solitons. I think quantum effects or effects that go beyond mean field theory have been seen in experiments, but let's look at how we can find these in the beta ansatz, from the beta ansatz, and how we can maybe make predictions for that. Okay, so now we have the same Hamiltonian as for the bright solitons, just positive value of G, and we use the beta ansatz in its original form, developed by, so written here down by Lieb and Liniger. And so many of you will be familiar on how that goes. So there's a wave function which is expressed by these quasi-momenta kj. There's one for each particle. And you find these self-consistently by solving this equation. There's a number of integer quantum numbers that you can put in there. And once you have these rapidities, you can calculate energy and momentum. And you can also calculate other things like form factors, which will actually become important. But let's just look at the spectrum for a minute. So if the number of particles is large, the spectrum is essentially dense in this green region. So here is momentum, here is energy. We're in a box with periodic boundary conditions. Here is a ground state, which I've subtracted, so it is 0. And then you have these blue dots, and they all lie on a parabola. So this is just translation from Galilean invariance. This is translation of the ground state by these momentum units, 2 pi h bar n, and these correspond to ring current states. So literally, essentially, a Galilean transformation of the ground state. Okay, and then there are elementary excitations. So particularly, we're interested here in these states which are called type 2 or yrast states. So we call them yrast as a jargon for the lowest energy state at given momentum. You may know that there are other elementary excitations that are phonon-like, and for example, the dynamic structure factor, which was mentioned here, came up in talks a couple of years ago, is mostly concentrated, at least for low interactions, on a phonon-like dispersion, which goes up this way. But we're interested in these lowest energy states. Okay, I mentioned the ring current, and we will look at these excitations. Now, so why do we look at these excitations? Because this dispersion relation, at least asymptotically, is congruent with the dispersion relation of dark solitons. Okay, so this was shown in this paper here in the 1980s. So we may hope to find some correspondence between these type 2 or hole type excitations in the Lieb-Lininger model with dark solitons. So in the thermodynamic limit, it comes right down here, and then you know, in a finite system, we have these Umklapp excitations here have finite energy. This is why you have a finite number of excitations that goes up there. Right. Now, there's been already quite a lot of work trying to explain how dark solitons, how the classical phenomena emerge actually then from these beta ansatz eigenstates. Now, one property that I mentioned here, I think, these eigenstates are translationally invariant. All of them are translationally invariant, right? They're momentum eigenstates. Okay, so you wouldn't expect them to actually show something that is a soliton, which is a dip in the density. Okay, so this is one question that comes up here. Now, there was some nice work by these authors here that shows that when you actually make a particle measurement in an experiment, how do you measure particles? There's one particle being detected by the detector, then the second particle is being detected by the detector, but the probability for the second particle, where to detect the second particle, is not given by the single particle density. It's given by a 4-point correlation function, right? Then detecting the third particle, again, it's a conditional probability because you've already detected the other two. It's given by a 6-point correlation function. So it's actually fairly high correlation functions that you need to generate what is given in a single shot measurement. And in this process, if you do that with the eigenstates of the Lieb-Lininger model, these solitons will emerge in that you see when detecting the last particle, essentially in that conditional probability, you will see the profile of the soliton. Yeah. So there was some other work here by Sato and collaborators that shows that localized density dip actually occurs if you make a superposition of all these yrast states. Okay, now, but they couldn't explain a lot of quantitative properties of these. So our proposal is now to make a Gaussian wave packet of yrast states in some you know, with some central momentum that we choose and some width in momentum here, and then look at these. So first of all, the soliton velocity is, and we do find that that is true, will then be given by the derivative of the energy with respect to momentum, dispersion relation. Okay, and now what do? We calculate the density as the time evolution of the density. Now we can do that because the form factors are known, which are here these overlaps of the beta ansatz eigenstates with different momenta here, P and Q. These different yrast states, we need them with a density operator at 0 position here. Right, so these P naught, they are our constructed Gaussian superposition states, and these are prefactors that go in there, and with this we can actually simulate the time evolution. So the result looks like this for one example. So we see something that looks like a dark soliton in the density. There is a dip. We see that it spreads in time and becomes more shallow. Yeah, so here is a trace of the position and the width as a function of time. Right, so now how to understand that? So in analogy to bright solitons, we can say, okay, you remember for bright solitons we have the center of mass separation, so we know that there is a center of mass which, if you localize it, it's a single particle free single particle wave function. If you localize it first, it will have to spread over time, just as a Gaussian wave packet does. So basically here we hypothesize that the same type of equations are relevant. So for the variance of the width of the density, single particle density, we propose that it's given by the sum of something that is time independent, which we call the fundamental soliton width, and the center of mass, and another component which we interpret as a variance of the center of mass, but this is now, it's not a real center of mass, which is just given by this formula. And so these are the definitions here. We have a number of particles, number of particle depletion, essentially, which we define as this sum over, over the missing density, essentially. Okay, so we can first of all propose these equations, and then we fit these two parameters, the fundamental soliton width and the mass. We fit that to the numerical simulations. Now, again, I wanted to, and the fits work very well. This is just demonstrating that these fits work very well. We, we just plotted them in a way that you always get straight lines and fitted straight lines, and that works very well. And it turns out that it all makes sense. Now, one question that I have here is, we just wrote this down because it seems to make sense. I think it is non-trivial, and in principle it should be possible to prove that out of the beta ansatz. Yeah, that this is what should happen. So if somebody who knows a lot about these things, is very clever, is in the audience, would be nice to have a mathematical proof of it. Okay, now, so the fundamental soliton width is one of the parameters that we extract here, and it's shown here in red as a function of gamma, which is the interaction, the coupling constant of the Lieb-Liniger model. So for very small gamma, what is recovered is the healing length, with a prefactor here that comes just from the way that we've defined this width parameter. So the dashed line here is the prediction from Gross-Pedersky theory. So that comes out well. Now for large gamma, this width parameter goes to 0. I think it's a fairly interesting and non-trivial quantity that we're extracting here, which is otherwise not easy to extract. Now you may remember from these formulas, you see so the width is not only given by this fundamental soliton width, but also by this time-dependent center of mass width, which depends on the depends on time, but depends also on the initial on some initial value, which is the width of this Gaussian wave packet, and that cannot be chosen completely arbitrary because we have only a finite momentum interval that is available. So there's sort of a minimum width that is available here, which is given by these blue dots. So and that, of course, will be much more important and will become dominant if you go into the strongly correlated regime. So so the sort of minimum width that you can make is eventually here just dominated essentially by linear physics, whereas as interesting nonlinear physics is then becomes just a small correction. Okay, some more things on this fundamental soliton width. So here we plotted it, we scaled it and plotted it as a function of nd. Now it turns out from Gross-Pedersky theory, the width can be, or this variance can be expressed entirely in terms of the interaction constant and nd, which is the number of depleted particles, and that completely includes the dependence that the soliton width has, for example, on velocity. Yeah, it does depend on velocity, but all this is already included in here. It seems that that is still the case for interacting in the interacting regime, and there's again an interesting deviation from the GP, the Gross-Pedersky or the nonlinear Schrödinger classical prediction in the limit where the missing number of particles becomes small. Yeah? So the interesting, or one thing that you can see here is when gamma becomes very small, actually, so ND, the negative number becomes large and negative, the solitons become macroscopic, but in the limit of strong correlations, Tong-Schur-Dou gas limit, the soliton, this number of particles just goes to -1. Okay, so that means in the limit, it is really just a single fermion hole, essentially. Yeah, so ND, as depending on momentum here, is plotted here again. So I apologize, there's no indications here of, these are for different interaction strength. So the line up here is for very strong interaction near the Tong-Schur-Dou limit. I think blue is probably for gamma equals 1, and this is more in the Gross-Bedevsky regime, or the weakly interacting Bogoliubov regime where gamma is small. Now okay, so ND, now I should say we can also obtain that from the dispersion relation of the Lieb-Liniger model, and we do, and it agrees with what we see in these numerical experiments. Another thing that we can calculate from the dispersion relations is the phase step. Okay, once we know MD, we know what the momentum is, we know what the velocity of the soliton is. From this, we can extract it from this formula. Okay, I will give an indication here on the next slide on where that comes from, but we extract something that is the phase step, which also for small gamma does essentially what is expected of it in terms of the nonlinear Schrödinger equation. For finite gamma, it does something different, but the soliton that sits here at momentum pi h bar n naught, that is the black soliton, that is the stationary soliton that has zero velocity. It always has a phase step of pi. Okay, so what does this phase step mean and where does it come from? The phase step, the way we calculate it or extract it is that we assume, okay, we have a soliton. Let me show that here. We have a soliton that has a density dip. Yeah, it's supposed to have a phase step. Now, if you want to fit that into a box with periodic boundary conditions, of course, that does not work. So in order to complete that around the ring, when the soliton is here, so what you have to do is you have to sort of add a background flow. Okay, so that is just a homogeneous flow phase gradient that then brings the phase back to come out at 0 or multiples of 2 pi. So, and that of course has to be, is given by the phase step divided by L and then h bar over n. Now, if you put these things into, okay, and then you can say, well, now we can look at, first of all, this is how we calculate it, and, well, or we calculate it from the momentum formula, actually, because then we say this corresponds to Galilean boost that you apply to the original system. Yeah? And then you can say, well, this has some consequence for the energy and for the momentum. Yeah? The momentum, because this is something we can calculate, we can extract delta from, and the energy we can use this formula to give a correction, and that works very well, right? So here is a thermodynamic limit dispersion relation, which we can calculate from the thermodynamic beta ansatz solution. The full line here is one that we calculated with the corrections that I just explained, and the dots are the actual solutions of the finite system with the beta ansatz. Okay, now this, so these here are the energy corrections. Now the logic behind applying these or deriving this formula for the energy correction rests on the fact that there is actually something like this phase step. Okay, now you should think, well, what does it actually mean? Now we have a one-dimensional Bose gas, it's interacting, it's supposed to have algebraic long-range order, there's no actual Bose-Einstein condensate in there, there's no finite, so there's no finite condensate in there, which means there should be no complex order parameter, there should be no phase. Or if there is phase, then maybe it is a fluctuating phase. Does it actually mean something? Yes, it does seem to mean something in terms of and the derivation assumes just that there is a phase step and that we need this this backflow current, which is a global thing. Yes, it applies over the whole ring. So, yeah, if somebody can explain to me what it means, that I would be interested to hear, but it seems that there is indication that it means something. Okay, so last but not least, I just want to show that we can also use the same technique to study soliton collisions. So again, this is full solutions of an interacting system with, I think in this case was 50 particles from the beta ansatz. One thing that you can see here is that in the collision, so you see the spreading of these wave packets, of course, but you also see that there is an offset, okay, which is expected to be there during due to the nonlinear interaction, essentially. So classical theory of solitons says that there should be some offset, and so we're still in the process of understanding that better. It seems that something interesting happens again if you crank on these interactions, whereas in classical limit is recovered for small interaction constant gamma. Okay, now how much time do I have actually? Is it already up or 5 minutes? Okay. Okay, so let's, it will be a shorter topic anyway, so let's try to do that in 5 minutes. So, what we want to do is we want to approximate a wave function for particles interacting many particle wave function with contact interactions by a Fock space expansion. So, what is a Fock space expansion? Superpositions of products of smooth single particle functions. Yeah, for fermions that could be slated determinants, or for bosons, permanents. Now, this is difficult to do. Okay, let's skip this slide. This is just some background. So we want to actually deal with Hamiltonians that look like this. So it's again very similar to before, but now let's assume that there may be some external potential which breaks integrability, so we can't use the beta ansatz. Okay, now the delta function that is in here, it produces a cusp in the wave function. So it can be written here in terms of beta Pyl's boundary conditions as something like this. So A is a scattering length and then an absolute value. And if you plot the wave function as a function here of the particle separation, you see the black line, that is what a cusp looks like. And then if you want to approximate this cusp with a product of plane waves, you know, this is just a Fourier transform of a cusp, and then you truncate it. That converges very slowly. Yeah. So the slow convergence actually is a real problem. Okay. So here's a result from some quantum chemists that try to use a harmonic oscillator basis to approximate fermionic wave functions, and they found that their energy error, for example, scales like 1 over square root of the number of basis functions, which is ridiculously slow. So we worked then with plane waves and found that there is a 1 over m scaling for the energy error, and you can do something which is renormalizing the coupling constant. Is something like, it's like essentially using a running coupling constant that improves this by 1 order. It's still slow, and of course the wave function won't become any better. Now, so what do we do about it? We want to basically build the correct boundary condition right in to the wave function. We do this by using a Jastrow factor, here e to the tau. So let's say this is the exact wave function. E to the tau is a function that is constructed like this by 2 particle wave functions that make sure that we have the correct boundary condition fulfilled. And then the idea is that this function phi, which remains here, which is basically defined by this equation, is something which is smooth and which is much simpler to approximate by, let's say, plane wave expansions. Right, so the way this works is if you plug this into the Schrödinger equation and then you multiply with e to the minus tau from the other side, you can write the equation in this form, and then becomes again a Schrödinger equation for this operator here, which we call the transcorrelated Hamiltonian. It's a similarity transformation of the original Hamiltonian, so it will have the same eigenvalue spectrum. And this goes back a long way to the 1960s in quantum chemistry. Bose and Handy originally proposed that. And it leads to some technical difficulties, but it's been known for a long time. Okay, now it is actually very nice, the similarity transform, if the taus are these factors that just depend on two-particle wave function, and can be shown to actually be reduced into this form. So, in addition to the Hamiltonian, because these these Jastrow factors, they commute with interactions and external potentials. You just have to commute them with kinetic energy. You have an explicit form. So you have additional terms to the Hamiltonian. One thing they do is they cancel the delta function interactions and generally provide something that is smoother. However, it's not Hermitian. The singular, and it has 2 and 3 body terms. Okay, now here is this correlation factor. So we need to find a function u that does a job for us. We found that one that can be very simply expressed in terms of its Fourier transform, and then in position it looks like that. It has one parameter which is a cutoff in momentum space, which sort of defines the size of this Jastrow factor. Yeah, now and then we use it, and we find that for two particles, for example, with attractive interactions, now that could be two bosons or a spin up and a spin down fermion, it works quite well. So here is the energy, so the difference of the energy to the exact energy. Yeah, so we're using here a system that is beta ansatz solvable, so we have the exact energy to compare with, and we see that, so the original direct diagonalization gives this energy error. The transcorrelated approach is here, and then on a log-log scale, you can see what is going on. In fact, what you see is the original diagonalization plane wave basis gives a slope of -1. Yeah, this is this 1 over m scaling of the energy error. Now, with renormalized approach, we get this one, and these are the transcorrelated approaches. These are the different size Jastrow factor, yeah, depending on the cutoffs. But asymptotically, they all go to this line, which has a slope of -3. Okay, so that is quite nice. So it's m to the -3. Scaling has improved quite a lot. Now, if you go beyond two particles, you have to take 3 particle terms from the transcorrelated Hamiltonian in principle into account. These are generated. They're sort of artifacts by the transformation that we do. And they do lead to errors, which can be seen here. So what we did is we solved the equations ignoring the 3-body term, and then we find that we get some, we just get some finite error. Yeah, so this doesn't go down. The error doesn't go down to 0, but it stays constant. We have some approximation, which I don't want to talk about very much. But then the nice thing is that you can actually avoid calculating this. So one thing you could do is you could just, bite the bullet and calculate these 3-body terms, and everything would be good. But you can actually get around calculating these 3-body terms in if you do the following. So this is actually what you see here. 3-body terms have different size, right? So if you adjust the size in such a way that, the Jastrow factors can have different sizes, and if you adjust the Jastrow factor such that it sort of becomes smaller range in position space as you expand your basis. Then as you expand the basis, basically what you're doing is you're sampling position space more closely. So, and if you make the Jastrow factor smaller, then the three-body interactions, these three-body terms will only be relevant on the short range. But you are having a dilute gas problem in principle, right? So, or yes, your number of sampling points will become larger, so it will become less and less dense, the problem. So, so what we do is we scale the cutoff of the Jastrow factor here with the maximum momentum that is in our basis. And if we do that with a factor that is 1/3 or smaller, we see that we can actually, even by ignoring these three-body terms, we can recover the scaling of m to the -3. Okay, let me not maybe dwell too much on these issues here because I know that I think time is running up. We have done that for 6 particles. It still seems to work. Maybe I want to mention that the wave function now becomes smaller. Yeah, so we've put this this boundary condition term in here into the Jastrow factor, and then if this is the exact wave function, that defines exactly what phi is, so we can look at what is the smoothness of the wave function. The original one has a cusp, so that is, it's C0, it is continuous but not differentiable. In momentum space, it's a k to the -2 dependence on for small k. The transcorrelated wave function becomes smoother now. So for bosons or two fermions, we can actually prove, and we also have checked that on examples, that this goes down to C2 or k to the -4. Yeah, so this is now twice differentiable and still continuous. Yeah, and then also, yeah. Now, for fermions, because there's less symmetry than for bosons, if you have more than 2 fermions, the smoothness is not improved quite so much, but it still goes to C1, and it's a k to the -3. So we have evidence for that in the momentum density. Now, the surprise that we have to some degree is here, that this transcorrelated Hamiltonian has this m to the -3 scaling, and that seems to be independent. It's the same for 2 particles, 2 bosons, for example, and for more fermions. Now, we have theoretical arguments that show, okay, we have proof essentially for this smoothness of the wave function. Now, the question is, what does that actually mean for improving the energy, the convergence of the energy? Now, for example, for 3 particles here, or for 6 particles, we should only really have an m to the -2, but we very clearly have an m to the -3, a slope of -3. So that is a little bit surprising. So the transcorrelated approach summary is it works very well, even for many particles, multiple particles, but we can't quite explain why it is as good as it is. I think with this, I think I should stop maybe and thank my collaborators. So the first project here was done with graduate student Sophie Shamailov, who is now accepted a postdoc position at the University of Auckland, and the second project was done while I was on sabbatical in Stuttgart at the Max Planck Institute for Solid State Research, and the group of Ali Alavi, who is here with collaborator Honjong Liu, and my graduate student Peter Jerzynski, who is also in the picture here. All right. Thank you for your attention. Yes. Yes. Yes, yes, and it does. It is essentially proportional to this number of depleted particles, this effective mass, by a factor of 2 to m, and in the limit where gamma, the linear coupling constant, goes to 0, this becomes large. This becomes macroscopic. Right, so the classical limit is fully retrieved by essentially gamma becoming small and this mass to become very large. Which just means that your spreading will happen at a much later time. Yes, and well, this way they could not access really, yeah, that's true. This way they could not access solitons with different velocity, with different parameter regimes, for example. And they see something which, of course, then spreads more quickly in time because it, yeah. I mean, they claim in their paper that what they have is exactly the soliton, but yeah. Sorry, is your question about the soliton, or is the question about? Oh, yes, good question. So it is important for the thing that we do, which is this: simulate the time evolution. Because there we just use the fact that the form factors are known and that we can actually solve the problem, and then we can simulate the time evolution, which otherwise we don't know how to do. This is for 100 particles. I mean, we could do it for 500 particles, and it is essentially exact. Now, for this theory, I don't think it matters. I think this is so. This is a guess anyway. This is not proof. This is not derived. This is just what I wrote down because I thought it must be true. And I don't see any reason for this not to be true if you have long-range interactions or any non-integrable case. Yes. In Tong-Shirado it becomes exact. Yeah. So in Tong-Shirado what happens is that sigma fs goes to 0. M is just the mass of a single fermion, and then it is a non-interacting Fermi. It's equivalent to a non-interacting Fermi gas. Yeah. So it is correct in that limit. Yeah. But for the interacting regime, we cannot prove it. Sorry, can you say that again? So, you want to take a superposition of what? Of all this? Oh, okay, but these are all the ring current states, right? So all the Umklaps, yeah. Yes. Now the answer is I don't know, because we haven't tried it. They are all translations of the ground state to some degree, right? So the internal structure of all of these states is the same. The only thing that changes is that it's an actual translation of the center of mass of the whole system. But all of them are translationally invariant. So I think you will probably get something which from the density perspective probably is boring. I assume the density will be flat at each time. Yes, I know. I still think it will be a flat density, but I don't know. Maybe maybe there would be some kind of interference pattern appearing there. But yeah, we can talk about this later. We could actually try. All right, thank you.